Hello there, and welcome to the Sleepy Library. Tonight, we are wandering into the magnificent realm of mountains, where ancient stone meets the endless sky in a timeless embrace of rock and silence. Mountains are more than just elevated terrain. They are the oldest storytellers on Earth, shaped by forces so patient and persistent that they measure time in millions of years. These towering guardians of stone hold within them the history of continents colliding, oceans rising and falling, and worlds that existed long before anything walked upon their slopes. Out there, across the planet, mountains reach toward clouds with peaks that have watched over the Earth for longer than we can truly comprehend. This is not just a journey through geology, it is a journey through peace, into the quiet majesty of places where time itself seems to slow down. The things we will discover are not only ancient, but beautifully real. These silent giants might change what we think we know about our planet, and remind us how small and brief our own existence truly is. If you enjoy these quiet journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, just breathe. Let the night sink around you and allow your mind to settle. Let us begin. Mountains are formed by the slow collision of tectonic plates beneath the Earth's surface. Deep below the ground we walk upon, enormous slabs of rock called tectonic plates float on a layer of partially molten stone. These plates move at the pace of fingernails growing, just a few centimeters each year. When two plates meet and push against each other, the immense pressure causes the crust to buckle and fold upward like a wrinkled blanket. This process creates mountain ranges that can stretch for thousands of miles. The Himalayan mountains formed when the Indian plate collided with the Eurasian plate, compressing the rock between them and pushing it skyward. This collision continues today, which means the Himalayas are still growing taller, though so slowly that no single human lifetime could measure the change. The force required to lift entire mountain ranges is almost beyond imagination. Yet, it happens through the gentle persistence of rock moving beneath our feet. Some mountains form through volcanic activity rather than collisions. When molten rock from deep within the Earth finds pathways to the surface, it erupts and builds layer upon layer of cooled lava and ash. Over time, these layers create mountains with steep sides and distinctive cone shapes. Mount Fuji in Japan formed this way, rising gracefully above the surrounding landscape as a perfect volcanic cone. These volcanic mountains can grow relatively quickly compared to collision mountains, building thousands of feet in just a few thousand years. Yet, even volcanic mountains require patience, as each eruption adds only small amounts of material and centuries can pass between significant events. The process is violent when active, but the result is serene, leaving behind mountains that stand as monuments to the Earth's inner fire. The Appalachian Mountains are among the oldest mountain ranges still standing on Earth. These gentle, rounded peaks in eastern North America began forming approximately 480 million years ago. The rocks exposed in the Appalachians date back even further, with some formations over 1 billion years old. When these mountains first rose, they may have been as tall as the Himalayas are today, with sharp peaks reaching high into the atmosphere. Over hundreds of millions of years, wind and water have worn them down. What remains are softer, more rounded summits covered in forests. The Appalachians have witnessed the rise and fall of entire ecosystems. the formation and splitting of supercontinents, and changes in climate that transformed the Earth multiple times. They have stood while entire oceans opened and closed, watching as life itself evolved from simple organisms to the complex creatures that now wander their slopes. Mountains create their own weather patterns through a process called orographic lifting. When wind carrying moisture approaches a mountain range, the air is forced upward along the slopes. As the air rises, it cools, and cooler air cannot hold as much moisture as warm air. The water vapor condenses into clouds, and if enough moisture accumulates, it falls as precipitation on the windward side of the mountain. This is why one side of a mountain range often receives abundant rainfall, while the other side remains dry. The Pacific Northwest receives heavy precipitation because moist air from the ocean rises over the coastal mountains and releases its water. On the opposite side, areas like the deserts of eastern Washington exist in what is called a rain shadow, where the air has already lost its moisture and descends as dry wind. Mountains quite literally shape the climate of entire regions simply by standing in the path of moving air. Snow that falls on mountains and does not melt becomes something more permanent over time. Fresh snow is light and fluffy, filled with air spaces between delicate ice crystals. When this snow survives through the summer without melting, it begins to transform. The weight of new snow falling on top compresses the older layers beneath, squeezing out the air and causing the ice crystals to grow larger and merge together. After about 1 year, this compressed snow becomes firn, a dense, granular material that is halfway between snow and ice. With more years and more pressure, firn continues to compact until it becomes glacier ice, which is so dense that it appears blue when light passes through it. This transformation can take anywhere from 3 to hundreds of years, depending on the temperature and the amount of snowfall. In the coldest regions like Antarctica, the process can take thousands of years. Glaciers are essentially rivers of ice that flow down mountains under their own tremendous weight, carving valleys and shaping the landscape as they move. Mountains host distinct layers of life that change with elevation. At the base of a mountain, the climate might be warm and wet, supporting lush forests. As you climb higher, the temperature drops approximately 6 degrees Celsius for every 1,000 meters of elevation gained. This cooling creates different ecological zones, stacked on top of each other like layers in a cake. Lower slopes might have deciduous forests with oak and maple trees. Higher up, these give way to coniferous forests of pine and spruce that can tolerate colder conditions. Above the tree line, where it becomes too cold for trees to survive, alpine meadows take over, filled with grasses and small flowering plants adapted to harsh winds and short growing seasons. At the very highest elevations, life becomes sparse, with only the hardiest mosses, lichens, and specially adapted insects able to survive. Climbing a single mountain is like traveling from one latitude to another, experiencing multiple climates without leaving the slope. The highest peak on Earth is not actually Mount Everest if you measure from the center of the planet. Mount Everest stands at 8,848 meters above sea level, making it the highest point you can stand on land. However, because the Earth is not a perfect sphere but bulges slightly at the equator, mountains located near the equator are actually farther from the Earth's center. Mount Chimborazo in Ecuador, while only 6,263 meters above sea level, is the farthest point from the Earth's center because it sits almost directly on the equator. This means the summit of Chimborazo is about 2,000 meters farther from the Earth's core than Everest's peak. Both measurements are correct, depending on how you define highest, and both mountains are magnificent in their own ways. These details remind us that even something as seemingly simple as height depends on perspective. Mountains accumulate and store vast amounts of water in the form of snow and ice. High peaks act like natural water towers, capturing precipitation and holding it frozen until warmer weather arrives. When spring and summer bring higher temperatures, the snow and ice gradually melt, releasing water in a steady flow that feeds rivers and streams. This meltwater is crucial for billions of people who live in lowlands far from the mountains themselves. The rivers originating in the Himalayas provide water to nearly 2 billion people across Asia. Mountain snowpack in the Sierra Nevada provides much of California's water supply. Without mountains capturing and slowly releasing precipitation, many rivers would flood violently during rainy seasons and run dry during droughts. Mountains regulate water flow across entire continents, distributing moisture through time and space in ways that make life possible. Regions that would otherwise be too dry to support large populations. Some mountains contain rocks that once formed the bottom of ancient oceans. When tectonic plates collide, sometimes the oceanic crust gets pushed upward rather than sliding beneath the continental plate. This brings rocks that formed underwater up to the surface, creating mountains made from ocean floor. The Himalayas contain limestone, formed from the shells and skeletons of marine creatures that lived in a warm, shallow sea millions of years ago. Today, you can find fossils of ancient sea creatures on some of the highest peaks on Earth. These fossils tell us that where mountains now stand, oceans once covered the land. The journey these rocks made from the seafloor to the top of the world required the movement of continents and the collision of land masses on a scale that reshaped the entire planet. The presence of seashells on mountain peaks reminds us that nothing on Earth is truly permanent, and what seems solid and unchanging is actually just a moment in geological time. Mountain glaciers are shrinking around the world as global temperatures rise. Glaciers form when more snow accumulates in winter than melts in summer, allowing ice to build up year after year. But when temperatures warm even slightly, the balance tips, and more ice melts than gets replaced. Studies show that mountain glaciers worldwide have been retreating for decades. Some small glaciers have disappeared entirely, while larger ones are thinning and pulling back up their valleys. This matters because glacial meltwater feeds rivers that supply water to millions of people during dry seasons. As glaciers shrink, the water supply they provide becomes less reliable. The changes happening to mountain glaciers serve as visible indicators of how Earth's climate is shifting, offering evidence that can be seen and measured without complex instruments. These rivers of ice have been flowing for thousands of years, and their retreat within a single human lifetime shows how quickly conditions can change. The tree line marks the elevation above which trees cannot survive. This boundary varies depending on latitude and local conditions, but it represents a fundamental limit to where trees can grow. Below the tree line, forests can thrive. Above it, only smaller plants survive. The tree line exists because temperatures drop with elevation, and at a certain point, it becomes too cold for trees to complete their growth cycle. The growing season becomes too short, and the trees cannot produce and store enough energy during the brief summer to survive the long, harsh winter. The average temperature of the warmest month needs to be around 10 degrees Celsius for trees to grow. Below this temperature, shrubs, grasses, and other low-growing plants take over. The tree line is not always a sharp boundary. Sometimes, trees gradually become smaller and more twisted as elevation increases, creating a transition zone where stunted, gnarled trees struggle at the edge of their survival range before giving way entirely to alpine tundra. Mountains can create their own unique weather systems called mountain waves. When stable air flows over a mountain range, it creates waves in the atmosphere, similar to waves in water flowing over a rock. These atmospheric waves can extend downwind for many miles, creating alternating bands of rising and sinking air. The rising air cools and can form distinctive lens-shaped clouds called lenticular clouds, which appear to hover in place even though wind is blowing through them. Pilots of small aircraft pay close attention to mountain waves because they can create severe turbulence and powerful downdrafts. Glider pilots, however, sometimes use these waves to gain altitude, riding the rising air to heights that would be impossible to reach by any other means. Mountain waves demonstrate how mountains influence the atmosphere far beyond their physical presence, creating patterns in the air that can be felt and seen for dozens of miles downwind. The Andes Mountains in South America are the longest mountain range on land, stretching approximately 7,000 kilometers along the western edge of the continent. These mountains, formed as the Nazca Oceanic Plate slides beneath the South American continental plate, a process called subduction. The descending oceanic plate melts as it sinks into the hot mantle, and some of this molten rock rises back toward the surface, creating the volcanoes that characterize much of the Andes. The range spans 7 countries and includes dozens of peaks over 6,000 meters tall. The Andes contain nearly every type of ecosystem, from tropical rainforests on their eastern slopes to some of the driest deserts on Earth on their western side. Indigenous peoples have lived in these mountains for thousands of years, developing sophisticated agricultural systems and building remarkable civilizations at elevations where the air is thin and growing crops is challenging. The ancient Inca Empire thrived in these mountains, creating terraced farms and stone cities that still stand today. Mountains experience more intense ultraviolet radiation than lowland areas. The atmosphere acts as a filter that blocks some of the sun's harmful UV rays, but the atmosphere becomes thinner with elevation. At high altitudes, there is less air above to filter the sunlight, so UV radiation intensity increases by approximately 10 to 12% for every 1,000 meters of elevation gain. This means that at the top of a tall mountain, the UV exposure can be twice as strong as at sea level. Plants and animals living at high elevations have adapted to this intense radiation. Alpine plants often have thick, waxy coatings on their leaves or dense coverings of fine hairs that help reflect and absorb UV light. Some produce protective pigments that give their leaves reddish or silvery colors. People who spend time at high elevations quickly notice the difference, as sunburn occurs much faster in the mountains than at sea level. The same sunlight that feels gentle in the lowlands becomes fierce and unforgiving on the peaks. Block mountains form when large sections of the Earth's crust fracture, and some blocks are pushed up while others drop down. Unlike fold mountains that form from compression, block mountains form from tension as the crust is pulled apart. The Sierra Nevada range in California is an excellent example of block mountains. Faults run along the eastern and western edges of the range, and the entire mountain block has been tilted, with the eastern side rising dramatically and the western side sloping more gradually. The eastern escarpment of the Sierra Nevada is one of the steepest mountain fronts in North America, rising nearly 3,000 meters from the valley floor in just a few miles. The valleys between block mountains are called grabens, and they often fill with sediment eroded from the mountains themselves. Over millions of years, these valleys can become deep basins filled with thousands of meters of accumulated rock and soil. Block mountains demonstrate that mountains can form not just from pushing together, but from pulling apart. Some mountains are so remote and difficult to access that they remained unnamed and unmapped until very recently. The mountain ranges of Antarctica covered by massive ice sheets, were largely unknown until the 20th century. Deep in the heart of Papua New Guinea, mountain peaks were only discovered by the outside world in the 1930s, when aerial surveys revealed valleys and ranges that had been home to indigenous peoples for thousands of years, but were completely unknown to modern geographers. Even today, with satellite imagery covering the entire planet, details about certain mountain regions remain incomplete. The remoteness of some mountains means they experience almost no human impact. These places exist in a state similar to what they might have been thousands of years ago, with ecosystems functioning without human interference. The difficulty of reaching these mountains preserves them, keeping them as refuges for species and landscapes that might otherwise have been altered by human activity. Mountain ranges can influence weather patterns thousands of miles away. The Tibetan Plateau, often called the roof of the world, is so massive that it affects atmospheric circulation across the entire northern hemisphere. During summer, the high elevation causes the land to heat up more than the surrounding lowlands. This creates a massive area of rising air that helps drive the Asian monsoon system, bringing seasonal rains to India, Southeast Asia, and parts of East Asia. Without the Tibetan Plateau, the monsoons would be much weaker, fundamentally changing the climate of regions home to billions of people. Similarly, the Rocky Mountains in North America affect weather systems moving from west to east across the continent, creating patterns of wet and dry zones that determine where forests grow and where grasslands or deserts form. These distant effects show how mountains are not isolated features, but integral parts of the planet's interconnected climate system. The rocks that make up mountains often contain minerals that slowly weather and break down over time. As rainwater, slightly acidic from dissolved carbon dioxide, trickles through cracks in the rocks, it gradually dissolves minerals, carrying them away in solution. This weathering process helps regulate Earth's climate over very long timescales. When silicate rocks weather, they consume carbon dioxide from the atmosphere and eventually lock it away in sediments on the ocean floor, where it can remain for millions of years. The Himalayas and other actively growing mountain ranges expose fresh rock surfaces to weathering, making them particularly important in this process. Some scientists believe that the rapid uplift of the Himalayas over the past 50 million years enhanced this weathering, drawing down enough atmospheric carbon dioxide to trigger a long-term cooling trend that eventually led to the ice ages. Mountains do not just shape the surface of the planet. They help regulate the composition of the atmosphere itself through chemical reactions so slow that they operate on geological timescales. Animals living at high elevations have remarkable adaptations for surviving in low oxygen conditions. Air pressure decreases with altitude, which means less oxygen is available with each breath. At the summit of Mount Everest, the air pressure is only about 1/3 of what it is at sea level, meaning each lungful of air contains far less oxygen. Humans visiting high altitudes often experience altitude sickness as their bodies struggle to get enough oxygen. But animals like the bar-headed goose have evolved to function normally at these heights. These geese migrate over the Himalayas, sometimes flying at altitudes exceeding 7,000 meters. They have larger lungs, more efficient hemoglobin for carrying oxygen, and denser networks of capillaries in their muscles compared to lowland species. Yaks, which live year-round on the Tibetan Plateau, have similar adaptations. Their hearts are enlarged to pump blood more efficiently, and their blood contains more red cells to carry oxygen. These adaptations developed over countless generations, showing how life finds ways to colonize even the most challenging environments. Some mountains are sacred to various cultures and religions around the world. Mount Kailash in Tibet is considered holy by 4 religions: Buddhism, Hinduism, Jainism, and the Bon religion. Pilgrims travel for weeks to circumambulate the mountain, walking around its base in a ritual that is believed to bring spiritual merit. Despite its religious significance, no one has climbed Mount Kailash, as doing so would be considered deeply disrespectful. Mount Fuji in Japan has been a sacred site for centuries, with Shinto shrines dotting its slopes and summit. Indigenous peoples in various parts of the world have long considered certain mountains to be dwelling places of spirits or ancestors. These sacred mountains often represent connections between earth and sky, between the human realm and the divine. The reverence people hold for these places shows how mountains occupy not just physical space, but also important positions in human spiritual and cultural landscapes. Mountains erode through several different processes working together. Freeze-thaw weathering occurs when water seeps into cracks in rocks, freezes overnight, and expands. Ice occupies more volume than liquid water, so the freezing process pushes outward on the crack walls, gradually widening the cracks until pieces of rock break free. This process is particularly effective in high mountains, where temperatures regularly oscillate above and below freezing. Glaciers erode mountains through 2 main processes: plucking and abrasion. Plucking occurs when glacial ice freezes onto rock fragments and tears them away as the glacier moves. Abrasion happens when rocks embedded in the bottom of a glacier scrape across bedrock like sandpaper, slowly grinding away the surface. Rivers also erode mountains by carrying away sediment and cutting deeper channels over time. The combined action of these processes gradually wears mountains down, but the process is so slow that it takes millions of years to lower a mountain range by even a few hundred meters. The Himalayas are still growing taller because the tectonic collision that formed them continues today. The Indian plate moves northward at a rate of about 5 centimeters per year, constantly pushing into the Eurasian plate. This ongoing collision compresses the rock between the plates, causing the mountains to rise. However, erosion from wind, water, and ice wears the mountains down at roughly the same rate they grow. This creates a kind of equilibrium, where the mountains maintain their height, but do not grow endlessly taller. The highest peaks of the Himalayas mark the point where the forces of uplift and erosion balance each other. Any rock pushed higher than this level gets eroded away faster than it rises. This balance has existed for millions of years, suggesting that the Himalayas may have reached their maximum height and will remain at approximately their current elevation until the tectonic collision that created them eventually ceases. Mountain valleys often contain layers of sediment that preserve records of past climates. As mountains erode, rivers carry sediment downstream and deposit it in valleys and basins. These deposits stack up in layers, with older layers on the bottom and younger layers on top. Scientists can drill cores through these sediment layers and analyze them to learn about past environments. Pollen grains preserved in the sediment reveal what plants were growing in the area. Changes in sediment type indicate whether the climate was wet or dry, warm or cold. Glacial sediments show when ice covered the area. By reading these layered records, researchers can reconstruct how climate has changed over thousands or millions of years. Some mountain valleys contain sediment records going back millions of years, offering windows into ancient worlds that no longer exist. These sediment archives help scientists understand natural climate variability and put recent changes into a longer perspective. The rain shadow effect can create deserts right next to some of the wettest places on Earth. The western slopes of the Cascade Range in Washington and Oregon receive enormous amounts of precipitation, with some areas getting over 3 meters of rain per year. But just on the other side of the mountains, the land becomes much drier. Eastern Washington receives less than 30 centimeters of precipitation annually in some places, creating a semi-arid climate that would qualify as desert if temperatures were slightly warmer. This dramatic difference occurs over a distance of less than 200 kilometers. All the moisture in the air gets wrung out on the western slopes, leaving the eastern side dry. Similar patterns occur in other mountain ranges around the world. The Atacama Desert in Chile, one of the driest places on Earth, exists in the rain shadow of the Andes. The Gobi Desert in Asia lies in the rain shadow of the Himalayas. These rain shadows can be so severe that they contain almost no vegetation, creating landscapes that look more like Mars than Earth. Mountain building and erosion play crucial roles in the rock cycle. When mountains form, they expose rocks that were once buried deep underground. These rocks, formed under intense heat and pressure, become subject to weathering and erosion once they reach the surface. As they break down, they produce sediments that wash into rivers and eventually reach the ocean, where they settle on the seafloor in layers. Over millions of years, these sediments get buried, compressed, and sometimes heated, transforming into new sedimentary rocks. If these sedimentary rocks get caught in another episode of mountain building, they can be buried even deeper, metamorphosing into entirely new types of rock, or even melting to form magma that may eventually cool into igneous rock. Mountains are essential to this cycle because they lift rocks from deep underground to the surface, where erosion can work on them, and they create the topographic relief that drives erosion in the first place. Some mountains contain valuable mineral deposits that formed through complex geological processes. When magma rises through the crust but cools before reaching the surface, it can form large bodies of intrusive igneous rock. As this rock cools slowly, minerals crystallize out of the liquid magma in a particular sequence depending on their melting points. Sometimes, hot fluids rich in dissolved metals migrate through cracks in the surrounding rock. When these fluids cool or react with the surrounding rock, the metals precipitate out, forming concentrated deposits of copper, gold, silver, lead, zinc, or other valuable elements. Mountain building can bring these buried mineral deposits closer to the surface, where they can be discovered and mined. The western United States has extensive mining districts in its mountain ranges, where mineral deposits formed tens of millions of years ago have been exposed by recent erosion. The presence of valuable minerals in mountains has driven exploration and settlement throughout human history. Alpine plants have fascinating adaptations for surviving extreme conditions. Many alpine flowers are surprisingly colorful despite the harsh environment. Bright colors help attract the few pollinators available at high elevations, mostly flies and bees that can tolerate cold temperatures. Many alpine plants grow in cushion or rosette forms, staying close to the ground where they avoid the worst of the wind and benefit from slightly warmer temperatures near the soil surface. Dark-colored leaves help some plants absorb more solar radiation, warming them above the ambient air temperature. Some alpine plants can even generate their own heat through metabolic processes, melting surrounding snow to create small growing spaces. Antifreeze compounds in their cells prevent ice crystals from forming and damaging tissues. Many alpine plants live for decades or even centuries, growing very slowly but persisting through conditions that would be rapidly fatal to lowland species. These adaptations allow flowering meadows to bloom briefly in the short alpine summer, creating bursts of color in an otherwise harsh landscape. Mountain streams and rivers are remarkably clear because they carry little dissolved material. Water in mountain streams is often so pure you can see every pebble on the bottom, even in deep pools. This clarity occurs because the water has had little time to dissolve minerals from rocks. Mountain streams also tend to be quite cold, as they are fed by snowmelt and springs emerging from underground. The cold temperature limits biological activity, so fewer algae and microorganisms grow in the water. The high gradient of mountain streams means they flow quickly, constantly refreshing and oxygenating the water. This high oxygen content supports fish species like trout that require clean, cold water to survive. As rivers leave the mountains and flow into lowlands, they warm up, slow down, and begin to carry more sediment and dissolved minerals, becoming less clear. But in their mountain origins, they represent some of the purest water found naturally on Earth. The summit of Mount Everest is not always the same elevation. The height of the mountain fluctuates slightly over time due to various factors. Tectonic movement causes the mountain to rise slowly. Earthquakes can sometimes change the elevation of peaks by shifting rock masses. The massive earthquake that struck Nepal in 2015 may have reduced Everest's height by a few centimeters, though the change was too small to measure conclusively with the technology available at the time. Survey teams from different countries have measured Everest multiple times over the past century, and the official height has changed several times, not always because the mountain itself changed, but because measurement techniques improved. The currently accepted height is 8,848 meters, agreed upon by China and Nepal in 2020 after a joint survey. But even this figure comes with uncertainty at the centimeter scale. The summit is also covered by snow whose depth varies, raising questions about whether the official height should refer to the rock beneath or the snow surface on top. Mountains create unique acoustic environments. The thin air at high elevations means sound travels differently than it does at sea level. Human voices carry for remarkable distances in the clear mountain air. But the sound may seem different because higher frequencies are absorbed more quickly. The presence of steep rock faces creates echoes, sometimes producing multiple reflections that make it difficult to determine where a sound originated. In deep mountain valleys, the walls can channel sound for long distances, allowing noises to be heard far from their source. Climbers have reported hearing conversations or sounds of equipment from groups hundreds of meters away. The quiet of remote mountain environments means there is little background noise to mask even faint sounds. At night in the mountains, silence can be profound, broken only by wind, the occasional falling rock, or the distant calls of nocturnal animals. This silence is increasingly rare in our modern world, making mountains valuable not just for their physical grandeur, but also for the experience of genuine quiet they provide. Permafrost, permanently frozen ground, occurs in many high mountain regions, even in temperate and subtropical latitudes. Permafrost forms when the average annual temperature remains below freezing, allowing ice to persist year-round in the soil. In mountains, permafrost can exist at elevations much lower than the permanent snowline, hidden beneath a thin layer of soil that thaws and refreezes seasonally. This frozen ground affects everything from what plants can grow to how water drains across the landscape. Permafrost provides stability to steep slopes by acting like cement, holding rocks and soil in place. As global temperatures rise, mountain permafrost has begun thawing in some areas. This thawing can destabilize slopes, increasing the risk of rockfalls and landslides. Mountain permafrost also contains trapped organic matter that begins decomposing when it thaws, releasing carbon dioxide and methane into the atmosphere. The thawing of mountain permafrost represents one of the many ways that climate change is affecting mountain environments in ways that may not be immediately visible but have significant consequences. The boundary between mountain and non-mountain terrain is not always clear. Geographers have proposed various definitions, but none is universally accepted. Some definitions focus on elevation, saying mountains must rise to a certain height above sea level. But this approach creates problems, because what counts as a mountain in one region might not in another. A hill in Colorado might be taller than a mountain in Scotland. Other definitions focus on relief, the difference in elevation between the base and summit. A feature with at least 300 meters of relief and certain slope requirements might qualify as a mountain, regardless of its absolute elevation. Some definitions incorporate isolation, considering a peak to be a mountain only if it is separated from higher peaks by a certain distance or drop in elevation. The lack of a universal definition means that lists of mountains vary, depending on the criteria used, and arguments about what is or is not a mountain can become surprisingly complex and contentious. Lichens are among the first organisms to colonize bare rock in harsh mountain environments. These organisms are actually symbiotic partnerships between fungi and algae or cyanobacteria. The fungus provides structure and protection, while the photosynthetic partner produces food through photosynthesis. Lichens can survive extreme cold, intense ultraviolet radiation, and long periods without water. They grow extremely slowly, sometimes adding only a millimeter or less per year. But given enough time, lichens can cover vast areas of rock in mountain regions. As they grow, they produce acids that gradually break down the rock surface, beginning the process of soil formation. Dead lichen material accumulates in cracks and crevices, providing foothold for mosses and eventually small plants. Over thousands of years, this process transforms bare rock into soil capable of supporting more complex plant communities. Lichens also serve as air quality indicators, as many species are sensitive to pollution and will not grow in areas with poor air quality. Their presence in remote mountains indicates environments that remain relatively pristine. Mountain ranges can affect human history and cultural development. The Alps separated the Mediterranean world from northern Europe for much of history, influencing the development of distinct cultures and languages on either side. The Himalayas formed a massive barrier between the Indian subcontinent and Central Asia, shaping trade routes and patterns of human migration. Mountain passes, the low points in mountain ranges, became crucial for travel and commerce. Control of strategic mountain passes could determine the outcomes of wars and the prosperity of nations. The Silk Road used several mountain passes to cross Central Asian ranges, facilitating cultural and economic exchange between East and West. Mountain barriers also provided protection, allowing isolated groups to maintain their languages, customs, and independence longer than they might have otherwise. The Basque people of the Pyrenees and many ethnic groups in the Caucasus Mountains maintained distinct identities, partly because mountain terrain made their homelands difficult to conquer or assimilate. Snow avalanches are a natural hazard in mountains that can release enormous amounts of energy. Avalanches occur when accumulated snow on a slope becomes unstable and slides downward. The instability can result from several factors: new snow adding weight to the snowpack, warming temperatures weakening bonds between snow layers, or the formation of weak layers within the snowpack. Some avalanches slide slowly, while others can accelerate to speeds exceeding 300 kilometers per hour, carrying thousands of tons of snow that devastates everything in its path. Large avalanches generate powerful air blasts that can demolish buildings hundreds of meters from the snow itself. The force of a major avalanche can snap mature trees like toothpicks and scour entire mountainsides down to bare ground. Despite their destructive power, avalanches play important ecological roles, creating openings in mountain forests and redistributing snow and nutrients. Areas frequently affected by avalanches develop distinctive vegetation patterns, with certain plant species adapted to surviving periodic burial and disturbance. The summit of a mountain may be thousands of years older or younger than its base. This statement seems paradoxical until you consider how mountains erode. If a mountain's summit consists of particularly resistant rock that erodes slowly, while the lower slopes are made of softer rock that erodes quickly, then even though the mountain as a whole is the same age, the rocks currently exposed at the summit may be much older than those exposed lower down. This is because the erosion has removed more material from the lower slopes, exposing younger rocks that were once buried deeper. Alternatively, if volcanic activity adds new material to a summit, the top of the mountain can be younger than its base. Mount Rainier in Washington has a summit composed of volcanic rocks that erupted in just the last 500,000 years, while the rocks at its base include much older formations. Understanding these relationships requires thinking about mountains not as static features, but as dynamic landscapes constantly being modified by erosion, weathering, and sometimes renewed volcanic or tectonic activity. Mountain goats and sheep have specialized hooves that give them remarkable climbing abilities. Their hooves have 2 separate toes that can spread apart for better grip, and the outer edges are hard, while the inner pads are soft and slightly concave, allowing them to grip onto small ledges and irregularities in the rock. These animals can walk along cliff faces that appear nearly vertical to human eyes, accessing feeding areas and escape terrain where predators cannot follow. Their center of gravity is low, and they have excellent balance, allowing them to make movements that seem impossible. Baby mountain goats can climb steep terrain within days of being born, a necessary ability because they are born in cliff habitats where predators are rare. These climbing adaptations allow mountain ungulates to exploit food resources that other herbivores cannot reach, avoiding competition and predation. Watching these animals move across seemingly impossible terrain is a reminder of how evolution can produce specialized abilities that perfectly match environmental challenges. Some mountains contain cave systems that extend deep into the earth. Limestone mountains are particularly prone to cave formation because limestone is soluble in slightly acidic water. Over thousands or millions of years, water percolating through cracks dissolves the rock, creating passages that can grow into massive cave systems. The longest cave system in the world, Mammoth Cave in Kentucky, has over 650 kilometers of surveyed passages, most of it within the remnants of an ancient mountain system. High-altitude caves present unique challenges for explorers, as they must deal with difficult climbing approaches in addition to the normal hazards of caving. Some caves in the Himalayas and other ranges have only been partially explored because of the extreme difficulty in reaching them. These caves preserve evidence of past climates, with formations like stalactites and stalagmites recording changes in temperature and precipitation over geological timescales. Ice caves, where permanent ice forms within the mountain, create strange and beautiful environments where winter conditions persist even during hot summers outside. The timberline, the upper elevation limit of tree growth, is not uniform around a mountain. Trees can grow higher on south-facing slopes in the northern hemisphere because those slopes receive more direct sunlight and are therefore warmer. North-facing slopes, receiving less sun, have lower timberlines. The timberline is also affected by local wind patterns, soil conditions, and moisture availability. In some places, trees extend higher up sheltered valleys, while stopping at lower elevations on exposed ridges where wind and cold are more severe. Near the timberline, trees often become stunted and deformed, growing in twisted shapes and remaining small even after many years. These krumholtz or crooked wood formations show trees at the absolute limit of survival. A tree that might grow tall and straight at lower elevations becomes a gnarled shrub at timberline, sometimes over 100 years old, but only a meter tall. The timberline creates a visible boundary on mountainsides, separating the green zone of forests from the browns and greys of the alpine tundra above. Mountain lakes often have incredibly clear water because they receive little sediment input. Lakes perched in mountain cirques or filling hollows carved by ancient glaciers may have no inflowing streams, receiving water only from snowmelt and precipitation. Without streams carrying sediment into them, these lakes can remain remarkably clear and blue. The cold temperatures at high elevations slow decomposition and limit algae growth, maintaining water clarity. Some mountain lakes are so clear that you can see down to depths of 20 meters or more. The stunning blue color of many mountain lakes results from the way pure water absorbs red light while scattering blue light back to our eyes. Mountain lakes provide critical habitat for specialized species adapted to cold, oligotrophic conditions. Some lakes freeze solid in winter or remain ice-covered for much of the year. The extreme conditions mean that mountain lake ecosystems are fragile and can be easily disrupted by pollution, climate change, or introduction of non-native species. The atmospheric pressure at the summit of Mount Everest is less than 1/3 of the pressure at sea level. This low pressure has profound effects beyond just making it hard to breathe. Water boils at a much lower temperature at high altitude because boiling occurs when water vapor pressure equals atmospheric pressure. At Everest's summit, water boils at about 71 degrees Celsius instead of 100 degrees. This makes cooking difficult and means that hot drinks cannot be as hot as at sea level. The low pressure also affects human physiology in multiple ways. Blood oxygen saturation drops to dangerous levels without supplemental oxygen. The body tries to compensate by breathing faster and producing more red blood cells. But these adaptations take time. Most people who climb Everest spend weeks at intermediate elevations, allowing their bodies to adapt gradually. Even with acclimatization, the summit is near the limit of human survival. The extremely low pressure means that in the so-called passing zone, above 8,000 meters, the human body is slowly failing, and staying too long at these elevations will eventually result in permanent harm or demise, regardless of acclimatization or fitness level. Mountains contain dramatic records of past ice ages in the form of glacial landforms. U-shaped valleys were carved by glaciers that flowed down mountainsides, bulldozing everything in their path and scouring the valley floors and walls into characteristic smooth, rounded shapes. Sharp ridges called artes form where glaciers erode two sides of a mountain simultaneously, leaving a knife-edge ridge between them. Bowl-shaped basins called cirques mark places where glaciers formed and began their descent. Moraines, piles of rocks and sediment, mark the farthest advance of glaciers or form along their sides where debris accumulated. These landforms tell us that ice once covered mountain ranges much more extensively than today. During the last glacial maximum, about 20,000 years ago, glaciers covered many mountains that are now ice-free. The landscapes left behind show the power of ice to reshape terrain, carving features in solid rock that reveal the past presence of glaciers long after the ice itself has melted away. Some mountains have been considered obstacles to be conquered, while others are revered and protected. Western mountaineering traditions often frame summiting peaks as achievements, using language of conquest and domination. But many cultures see mountains as sacred spaces that should not be climbed or disturbed. This difference in perspective has led to conflicts when climbers from one cultural tradition wish to summit peaks that other cultures consider sacred. Mount Everest is called Sagarmatha in Nepal and Chomolungma in Tibet, names that carry spiritual significance ignored by the English name honoring a British surveyor. The question of who has the right to name mountains and whether climbing them is appropriate reflects broader issues about respecting indigenous cultures and recognizing that Western perspectives are not universal. Mountains can be many things: challenges to be overcome, sacred spaces, homes, watersheds, refuges for endangered species, or simply beautiful features to be appreciated from a distance. Lightning strikes mountain peaks more frequently than low-lying areas. Tall peaks project into the atmosphere and become natural lightning rods during storms. The probability of being struck by lightning increases with elevation, because you are literally getting closer to the clouds where lightning forms. Mountains can also trigger the formation of thunderstorms by forcing air to rise rapidly, creating conditions favorable for lightning. Being caught in a thunderstorm on an exposed mountain ridge or summit is extremely dangerous. Rock provides little protection from lightning, and there may be no shelter for kilometers. Metal equipment, like climbing gear, can conduct electricity. Many mountaineers have been struck by lightning, sometimes fatally. The electrical charge from a lightning strike can travel through rock for dozens of meters, meaning you do not have to be directly struck to be harmed. During a thunderstorm, the safest location is often far from the summit, in a low area away from tall features. But this may not be reachable if you are caught near the top when a storm develops. Mountain weather can change rapidly, with calm, sunny conditions giving way to violent thunderstorms in less than an hour. Mountains can generate their own weather, even when the surrounding lowlands are clear. As the sun heats mountain slopes during the day, the warmed air rises along the mountainsides. This rising air carries moisture upward, where it cools and condenses into clouds. By afternoon, mountains often wear caps or collars of clouds, even when the valleys below remain clear. These mountain clouds can produce rain or snow that falls on the peaks while lowlands remain dry. At night, the process reverses. Mountain slopes cool rapidly through radiational cooling, and the cold, dense air flows downslope into valleys, sometimes creating fog in valley bottoms while peaks remain clear. These daily cycles of heating and cooling create regular weather patterns in many mountain regions. The ability of mountains to generate their own weather means that mountain environments can have significantly different conditions than nearby lowlands, even when the regional weather patterns are similar. The highest permanent human settlements on Earth exist in mountains. The village of La Rinconada in Peru sits at approximately 5,100 meters elevation, where the thin air makes even walking difficult and the cold is nearly constant. People live there because gold mining provides economic opportunities that do not exist in the lowlands. The Himalayan regions of Tibet, Nepal, and Bhutan contain communities at elevations above 4,000 meters, where people have adapted to the thin air over many generations. These high-altitude populations have genetic adaptations that help them function with less oxygen than lowland people require. Larger lung capacity, greater blood flow, and more efficient use of oxygen all contribute to their ability to live and work at elevations where visitors struggle just to breathe normally. Life in these environments is challenging, with short growing seasons, cold temperatures, and isolation from lowland areas. Yet people have made homes in these places for thousands of years, developing unique cultures adapted to mountain life. Mountain ranges affect climate not just locally, but across entire hemispheres. The formation of the Himalayas, beginning around 50 million years ago, changed global climate patterns by altering atmospheric circulation and increasing weathering rates that drew carbon dioxide from the atmosphere. Some scientists believe the uplift of the Himalayas contributed to global cooling that eventually led to the ice ages. The Andes affect El Niño and La Niña patterns by blocking and redirecting atmospheric circulation over South America. The mountains of Antarctica channel ice flow from the interior to the coast, affecting how much ice enters the ocean and therefore sea levels. These global effects show that mountains are not just passive landscape features, but active components of Earth's climate system. Changes to mountain environments through erosion, tectonic uplift, or glacial advance and retreat can have consequences that ripple through the entire planetary system, affecting weather patterns, ocean currents, and atmospheric composition in ways that scientists are still working to fully understand. Mountains are eroding, and in some cases, rising simultaneously, creating dynamic equilibrium. The Himalayas rise about 5 millimeters per year on average, due to the ongoing collision between India and Asia. But erosion removes rock at about the same rate. Rivers cutting through the mountains carry millions of tons of sediment every year, wearing away the peaks even as tectonic forces push them up. This balance between uplift and erosion can persist for millions of years, maintaining mountain ranges at relatively constant heights, even though the individual rocks at the surface are constantly being replaced. Without erosion, mountains would continue to grow indefinitely until they collapsed under their own weight. Without uplift, erosion would eventually reduce all continents to sea level. The interplay between these opposing processes shapes landscapes and determines where mountains exist, how high they stand, and how long they persist. Understanding this balance helps geologists predict how mountain ranges will change over geological timescales, and how human activities like deforestation, which accelerates erosion, might affect mountain landscapes. Mountain soils are often thin and poor in nutrients compared to lowland soils. On steep slopes, gravity constantly pulls soil downward, preventing deep accumulation. Heavy rains can wash away topsoil before it has time to develop. The cold temperatures at high elevations slow the decomposition of organic matter, meaning nutrients are released more slowly from dead plant material. Despite these challenges, mountain soils support diverse plant communities through careful adaptations. Many mountain plants have extensive root systems that spread horizontally to capture nutrients and anchor the plant against erosion. Nitrogen-fixing plants form partnerships with bacteria that can capture nitrogen from the air, providing this essential nutrient even when soil nitrogen is scarce. The thin soils mean that what little accumulates is precious, and disturbances that remove soil can take decades or centuries to heal. Mountain ecosystems are fundamentally limited by soil, and the slow pace of soil formation at high elevations means that recovery from damage is measured in human lifetimes rather than seasons. Glaciers contain air bubbles trapped when snow compressed into ice thousands of years ago. These tiny bubbles preserve samples of the ancient atmosphere, allowing scientists to study past atmospheric composition. By drilling ice cores from glaciers and ice sheets, researchers can extract these bubbles and analyze the air inside. The bubbles reveal how much carbon dioxide, methane, and other gases were in the atmosphere when the snow fell. Ice cores from Antarctica have been drilled to depths of over 3 kilometers, retrieving ice nearly 1 million years old. The air bubbles in this ice tell us about climates before humans existed, showing natural cycles of warm and cold periods. This information helps scientists understand how the climate system works and provides context for evaluating modern climate changes. The ice itself also contains information, with layers of dust, volcanic ash, and chemical traces that mark significant events in Earth's history. Glaciers are frozen libraries, preserving evidence that would be destroyed by weathering if it remained at the surface. Mountain meadows bloom, with stunning displays of wildflowers during brief growing seasons. After months buried under snow, these meadows explode with color in just a few weeks, as dozens of species flower simultaneously. This synchronization happens because the growing season is so short that plants cannot afford to spread their flowering over months like lowland species do. Everyone must bloom, get pollinated, and set seed before winter returns. The result is carpets of flowers, creating a kaleidoscope of colors across alpine slopes. Blue lupines, red paintbrush, white avalanche lilies, and yellow buttercups paint mountainsides in patterns that shift with elevation and exposure. These flower displays attract pollinators from miles around, and the meadows buzz with activity during the short summer. Many alpine flowers can track the sun, rotating to follow it across the sky, maximizing the light they capture during the precious warm hours. Some can even generate heat, warming themselves several degrees above air temperature to speed growth and attract pollinators. The brief intensity of mountain bloom cycles creates moments of beauty that feel almost urgent, as if the plants know their window of opportunity is fleeting. Rivers that originate in mountains have distinctive characteristics. Mountain rivers are typically cold, fast-flowing, and highly oxygenated. The steep gradients cause water to rush downward with tremendous energy, carving deep channels and moving large rocks that lowland rivers could never budge. The turbulent flow incorporates air into the water, increasing oxygen levels to near saturation. This combination of cold temperature and high oxygen supports fish species with high metabolic demands, like trout and salmon. Mountain rivers also experience dramatic seasonal variations in flow. During spring snowmelt, rivers can swell to many times their winter volume, becoming powerful torrents that reshape their channels, moving boulders and cutting new paths. By late summer, flows diminish to clear, gentle streams where you can see every stone. This seasonal pattern has shaped the ecology and human use of mountain rivers for thousands of years. Communities that depend on mountain rivers must accommodate these extremes, living with abundance during snowmelt and scarcity during late summer. The formation of fold mountains involves rocks behaving in ways that seem impossible. When we see rocks in everyday life, they appear brittle and inflexible. But under the immense pressure and heat deep in the Earth's crust during mountain building, rocks can bend and flow like warm plastic. Layers of sedimentary rock that were originally deposited horizontally get folded into waves, arches, and complex curves. Some folds are gentle undulations spanning kilometers. Others are tight and dramatic, with rock layers bent back on themselves. The core of many mountain ranges contains these folded rocks, visible in road cuts and cliff faces, where the curved layers paint swirling patterns across the exposed surface. Understanding how rocks can fold rather than break helps geologists reconstruct the forces that created mountains and determine how much compression occurred during mountain building. The folded rocks are not just beautiful, they are records of the immense forces that shaped the continents. Mountain forests differ from lowland forests in many subtle ways. Trees grow more slowly at high elevations, producing narrower growth rings because the growing season is shorter and conditions are harsher. This slow growth creates dense wood with properties that made mountain timber valuable for construction and musical instruments. The trees themselves are often smaller at high elevations than their lowland relatives of the same species, adapting to cold and wind by remaining compact. Forest composition changes with elevation, with different tree species dominating at different heights. Lower slopes might have mixed deciduous conifer forests. Mid-elevations often feature pure stands of conifer species adapted to moderate cold and snow. Near timberline, only the hardiest conifers survive, often growing in scattered groves rather than continuous forests. The understory plants also change with elevation, tracking the temperature and moisture gradients. These elevational bands create habitat diversity over short horizontal distances, supporting different animal communities at each elevation. A mountain can contain as much ecological diversity along its slopes as you would encounter traveling hundreds of kilometers across flat terrain. Some mountains contain extensive mineral deposits that formed from hydrothermal systems. When magma intrudes into the crust, it heats surrounding rocks and any water present. This hot water becomes a powerful solvent, dissolving minerals from the surrounding rock. As this mineral-rich fluid moves through cracks and porous rock, changes in temperature, pressure, or chemical conditions can cause dissolved metals to precipitate out, forming concentrated ore deposits. The mountain ranges of the western United States contain numerous deposits of gold, silver, copper, and other metals that formed this way millions of years ago. Mining these deposits has shaped the history and economy of entire regions. The same hydrothermal processes can create hot springs at the surface, where heated water emerges, sometimes carrying dissolved minerals that precipitate to form colorful terraces and deposits around the springs. These geothermal features are windows into the heat engine beneath mountains, places where the mountain's inner warmth reaches the surface in tangible ways. Cloud forests represent a unique mountain ecosystem found in tropical and subtropical regions. These forests exist at elevations where clouds regularly envelop the mountains, bathing the vegetation in constant mist. Persistent moisture allows epiphytic plants like orchids, bromeliads, mosses and ferns to cover every surface. Trees in cloud forests are often shorter and more gnarled than rainforest trees at lower elevations, their branches heavy with epiphytes that create miniature ecosystems. The constant fog provides moisture that plants can absorb directly through their leaves, supplementing water uptake from roots. Cloud forests harbor extraordinary biodiversity, with many species found nowhere else. The Monteverde cloud forest in Costa Rica, the cloud forests of the Andes, and similar ecosystems in Southeast Asia and Africa contain countless species of plants, insects, amphibians and birds adapted to these misty worlds. Cloud forests also play crucial roles in water cycles, capturing moisture from passing clouds and channeling it into streams that supply water to lowlands. As climate changes alter cloud patterns, some cloud forests are experiencing less fog, threatening both the ecosystems and the water supplies they provide. Talus slopes, accumulations of broken rock at the base of cliffs, are dynamic features constantly in motion. Rocks broken from cliff faces by freeze-thaw cycles, lightning strikes, or simply time tumble down and accumulate in characteristic cone-shaped piles. The newest rocks rest near the surface, while older material is buried beneath. Talus slopes may appear static, but they are actually creeping slowly downslope under the influence of gravity. Heavy rains can trigger rapid movements, where entire sections of talus flow downward, like frozen waterfalls suddenly melting. Small rockfalls add individual stones regularly, creating a constant patter of sound during warm days when ice melts and rocks are released. Animals have adapted to life on talus slopes, despite the unstable surface. Pikas, small relatives of rabbits, live among the rocks, collecting vegetation and storing it for winter. Marmots den beneath boulders, where spaces between rocks provide shelter. These rocky environments seem inhospitable, but they support specialized communities adapted to life on the mountain's broken bones. The color of mountain water can reveal its origins. Glacial meltwater often appears milky blue or gray because it contains rock flour, extremely fine sediment ground from bedrock by the glacier's immense weight and movement. This suspended sediment reflects light in ways that give the water its distinctive color. Lakes fed by glacial meltwater often share this milky appearance. Springs emerging from deep within mountains typically run crystal clear because the water has filtered through rock, leaving sediment behind. During heavy rains, mountain streams can suddenly turn brown, with suspended sediment washed from slopes. The color changes tell stories about what is happening upstream, whether glaciers are actively melting, whether rain has destabilized soil, or whether the water is emerging from deep underground. Observant viewers can read these liquid stories, understanding the mountain's behavior through the appearance of its waters. Some mountains experience temperature inversions, where cold air pools in valleys while higher elevations remain warmer. On calm, clear nights, the mountain slopes radiate heat to space and cool rapidly. The cold, dense air flows downslope and settles in valleys, creating pockets of frigid air, while the upper slopes remain relatively mild. These inversions can persist for days, especially in winter, creating situations where valley floors are freezing, while locations 1,000 meters higher enjoy comfortable temperatures. Temperature inversions affect where people choose to live and where certain crops can be grown. In some mountain regions, vineyards and orchards occupy slopes above valley floors to avoid frost damage. The inversions also trap air pollution in valleys, where it cannot disperse until weather patterns change and mix the atmosphere. Understanding these temperature patterns is crucial for anyone living in or traveling through mountain regions, as conditions can vary dramatically over short distances. Kromholz, the twisted, stunted trees at timberline, tell stories of survival against overwhelming odds. These trees may be over a century old, but stand only waist-high, their growth slowed by cold, wind, and short growing seasons. Many grow flagged, with branches extending only on the lee side, where they are sheltered from prevailing winds. The windward side gets pruned back by wind-driven ice crystals that abrade and kill exposed buds. Snow provides insulation in winter, so branches buried under snow survive, while those exposed to winter winds perish. The result is trees that grow more outward than upward, spreading across the ground like woody mats. Some Kromholz forests consist of what appear to be separate trees, but are actually branches from a single individual that has spread vegetatively, creating clones connected underground. These resilient trees mark the absolute limit of where tree-form plants can survive, living at the boundary between two worlds. The study of tree rings from mountain trees provides detailed climate records. Each year, a tree adds a growth ring, and the width of that ring reflects growing conditions. Wet years with long growing seasons produce wide rings. Dry or cold years produce narrow rings. By examining cores extracted from old trees, scientists can reconstruct precipitation and temperature patterns going back centuries or even millennia. Mountain trees are particularly valuable for this research because they are often stressed by conditions near their limits, making them sensitive recorders of climate variations. The longest-lived trees provide the longest records. Bristlecone pines in the mountains of California and Nevada can live over 4,000 years, making them among the oldest individual organisms on Earth. Tree ring studies from these ancient trees have revealed details about droughts, temperature fluctuations, and climate patterns that occurred thousands of years ago, long before any written records existed. These trees are living archives, silently recording Earth's climate history in their wood. Glacial lakes often have no visible outlet, yet maintain relatively constant levels. These lakes receive water from melting glaciers and snow, yet seem not to lose water through any stream. The water exits through underground pathways, seeping through the rock or soil and emerging as springs at lower elevations. Sometimes these underground flows carve channels through soft rock or between rock layers, creating hidden river systems beneath the mountain. The underground water may travel for kilometers before emerging, often where geological conditions create barriers that force the water to the surface. These hidden waterways are difficult to study because they are inaccessible. But dye tracing studies have revealed their existence by coloring lake water and then finding the dye emerging from springs far downslope. The hidden connections between mountain waters remind us that what we see on the surface is only part of the story. Nevel zones, the highest elevations of mountains where snow and ice dominate and vegetation is virtually absent, represent some of Earth's most extreme environments. These zones exist above the snowline, where temperatures remain below freezing most of the year. Life here is sparse, limited to hardy lichens growing on rock surfaces, occasional mosses in protected spots, and insects blown up from lower elevations. The landscape consists of rock, snow, and ice, sculpted by wind and temperature extremes. Summer warming may expose rock surfaces for brief periods, but conditions remain harsh. Temperatures can fluctuate widely, dropping far below freezing at night and climbing above freezing during sunny days, creating cycles of freezing and thawing that gradually break rocks apart. The Nevel Zone is a place of austere beauty, where the mountain reveals its most fundamental nature as rock and ice meeting sky. Some mountain peaks are pyramidal, shaped by glaciers that eroded multiple sides simultaneously. The Matterhorn in the Alps exemplifies this form, with 4 steep faces meeting at a sharp summit. This shape develops when glaciers flow down several valleys radiating from a central peak. Each glacier erodes the mountainside, steepening the faces and sharpening the ridges between them. Over time, the peak becomes increasingly pointed and dramatic. The formation of pyramidal peaks requires specific conditions: a central high point with valleys radiating outward, sufficient ice to maintain glaciers in multiple valleys, and enough time for erosion to shape the peak. Not all mountains develop this form, but those that do create some of the most visually striking peaks in the world. These shaped summits stand as monuments to the sculpting power of ice, their forms determined by frozen rivers that carved them over millennia. Mountain passes have been routes of human travel and trade for thousands of years. These low points in mountain ranges offer the easiest paths across barriers that would otherwise be nearly impassable. Historic trade routes followed mountain passes, even when the journeys were long and difficult, because the alternative was far worse. The Silk Road used passes through the mountains of Central Asia. Armies marched through passes like the Brenner Pass in the Alps and the Khyber Pass in the Hindu Kush. Indigenous peoples throughout the Americas used mountain passes for seasonal migrations, trade, and communication between groups on opposite sides of ranges. Many modern highways follow routes established centuries or millennia ago, demonstrating that the geography of mountain passes exerts lasting influence on human affairs. Control of strategic passes could determine the fate of nations, and many historical conflicts centered on securing these critical corridors through otherwise impassable terrain. The specific heat capacity of rock affects mountain microclimates. During the day, Exposed rock surfaces absorb solar radiation and become much warmer than the air. Dark-colored rocks can reach temperatures hot enough to burn skin, even when air temperature is comfortable. At night, these same rocks radiate their stored heat back to space, cooling rapidly. This daily cycle creates microclimates around rock features. Crevices between boulders can be warm refuges during cold nights, heated by the rock's stored warmth. By day, shaded spots between rocks offer cool shelter from intense sun. Plants and animals use these microclimate variations to extend their ranges higher or persist in conditions that would otherwise be intolerable. Seeds germinating on the warm side of a boulder have different survival prospects than those on the cold side. These small-scale temperature variations create a mosaic of conditions, multiplying habitat diversity and allowing species to find suitable spots even in generally harsh environments. Mountain building on Earth differs from mountain formation on other planets. Mars has the tallest mountain in the solar system, Olympus Mons, a volcanic peak over 21 kilometers high. This mountain grew so tall partly because Mars lacks plate tectonics. On Earth, moving tectonic plates eventually carry volcanic mountains away from their magma sources, limiting their growth. On Mars, volcanic hotspots remain stationary, allowing mountains to build for millions of years uninterrupted. The Moon has mountains formed by asteroid impacts, their peaks and ridges surrounding massive craters. These mountains were created in moments rather than gradually. Venus has mountains formed by volcanic activity and possibly by crustal deformation, though the planet's extreme heat makes detailed study difficult. Earth's mountains are unique in being constantly modified by water erosion, plate tectonics, and biological activity. The presence of life, weather, and dynamic geology makes Earth's mountains particularly complex and ever-changing, compared to the static peaks of airless bodies or the purely volcanic constructs of planets without plate tectonics. Alpine animals often undergo dramatic seasonal changes. Mountain goats grow thick winter coats that they shed in ragged patches during summer, transforming their appearance completely. Ptarmigan change plumage color from mottled brown in summer to pure white in winter, providing camouflage against changing backgrounds. Some animals migrate vertically rather than horizontally, moving to lower elevations for winter and returning to high country for summer. Elk in the Rocky Mountains winter in valleys and summer in alpine meadows. This migration allows them to follow the growing season upslope, accessing fresh vegetation as it emerges. Other animals hibernate, avoiding winter entirely by sleeping in burrows insulated by snow. Marmots spend over half their lives in hibernation, emerging only during the brief mountain summer to feed, breed, and store fat for the next winter. These adaptations reflect the extreme seasonality of mountain environments, where the difference between summer and winter represents the difference between abundance and hardship. Mountain shadows can extend for hundreds of kilometers, affecting weather and climate far from the peaks themselves. When the sun is low on the horizon, tall mountains cast shadows that stretch across vast distances. In winter, at high latitudes, mountain shadows can persist for hours, keeping valleys in twilight, while surrounding lowlands bask in sunlight. These shadows affect temperature, frost formation, and the timing of snowmelt. In some steep valleys, the sun may not reach the valley floor at all during winter months, creating perpetual shadow that keeps temperatures low and snow persistent. The psychological effects of living in such shadow can be significant, and some communities have installed mirrors on mountainsides to reflect sunlight into valley towns during the darkest months. The dance between mountains and light creates patterns of warmth and cold, brightness and shadow that shape both physical environments and human experiences. Fossil evidence from mountains reveals ecosystems that existed millions of years ago. Sedimentary rocks in mountain ranges sometimes contain fossils of plants and animals that lived when the rock formed as mud or sand at the bottom of ancient seas or lakes. The uplift that created the mountains brought these fossils from their underwater origins to mountaintops. Paleontologists have found marine fossils, including shells, corals, and fish, on some of the highest peaks. These fossils help scientists understand what conditions were like in the past and how the planet has changed. Some mountain rocks contain fossils of tropical plants that grew when the rocks were located at different latitudes before tectonic movements carried them to their current positions. These fossil assemblages are puzzles that help reconstruct the past, showing us worlds that vanished long ago but left their traces in the stones that now form mountains. The movement of water through mountain landscapes follows intricate pathways. Rain and snowmelt can follow multiple routes to lower elevations. Some water flows over the surface as streams, visible and immediate. Other water infiltrates into the soil and moves slowly through tiny pores between soil particles. Still more water seeps deeper, entering cracks in bedrock and traveling through underground passages that may extend for miles. The proportion taking each pathway depends on soil depth, rock type, slope angle, and how much water is available. During intense rainfall, the soil may become saturated, forcing more water to flow over land. During gentle rain or snowmelt, most water may infiltrate. This partitioning of water between pathways affects flood risk, water quality, and how reliably streams flow during dry periods. Mountain watersheds with deep soils and permeable rock act as giant sponges, absorbing precipitation and releasing it gradually. Those with thin soils and impermeable rock shed water quickly, creating flashy streams that flood easily and dry up rapidly. Snow metamorphosis transforms the structure of snowflakes after they land. The intricate six-sided crystals that fall from clouds begin changing immediately upon deposition. Temperature gradients within the snowpack cause water molecules to migrate from smaller ice grains to larger ones. Sharp points sublime away, and the vapor redeposits in hollows and on larger grains. Over days and weeks, the feathery snowflakes become rounded grains, then larger faceted crystals, and eventually may form weak layers within the snowpack that can trigger avalanches. Understanding snow metamorphosis is crucial for avalanche forecasting. Certain crystal types create particularly unstable layers. When these weak layers are buried under heavier snow, they can fail, releasing avalanches. The science of snow is complex, with dozens of recognized crystal types and transformation pathways. What appears to casual observers as simply snow is actually a dynamic material, constantly changing in response to temperature, pressure, and time. Mountains concentrate biodiversity in ways that create hotspots of species richness. The varied elevations, slopes, exposures, and microclimates within mountain regions provide enormous habitat diversity in small areas. Different species adapted to different conditions can all find suitable habitats somewhere on the mountain. The isolation of mountain ranges also promotes speciation, as populations separated on different mountains or in different valleys evolve independently. Cloud forests in tropical mountains harbor extraordinary numbers of endemic species found nowhere else on Earth. The mountains of New Guinea, the tropical Andes, and East African highlands rank among the most biodiverse regions on the planet. Even temperate mountains support impressive diversity. The Great Smoky Mountains in Tennessee and North Carolina host more tree species than all of Europe. This diversity makes mountains irreplaceable reservoirs of genetic variation and evolutionary potential, places where nature experiments with form and function in countless variations. The angle of repose, the steepest slope at which loose material remains stable, determines the maximum steepness of talus slopes and other unconsolidated material. For most rock fragments, this angle is between 30 and 40 degrees from horizontal. Slopes steeper than this cannot maintain loose material, which slides or rolls down until the slope reaches a stable angle. This physical principle creates characteristic slope angles on talus piles, scree slopes, and other accumulations of broken rock. The consistency of these angles across different mountains and regions reflects fundamental physics rather than local conditions. However, the specific angle of repose varies slightly depending on particle size, shape, and moisture. Dry sand has a different angle of repose than wet sand or angular rock fragments. Understanding angle of repose helps geologists interpret landscape features, and engineers design stable structures on steep terrain. Mountain streams create distinctive sounds that become part of the auditory landscape. The tumbling of water over rocks produces a complex acoustic signature that changes with flow rate, channel geometry, and rock size. High flows during snowmelt create continuous roaring as water rushes through rapids and plunges over falls. Lower flows produce more musical sounds, gurgling and splashing, that vary from place to place along the stream. People who spend time in mountains often find these water sounds soothing, and many seek them out deliberately. The white noise of rushing water masks other sounds and can facilitate relaxation or sleep. The constancy of stream sounds provides acoustic continuity through day and night, a natural soundtrack to mountain environments. These sounds are also informational, telling careful listeners about water levels, the character of the streambed, and whether flow is increasing or decreasing. Subduction zones, where oceanic plates sink beneath continental plates, create some of the most spectacular mountain ranges. The Andes formed this way as the Nazca Plate subducts beneath South America. As the oceanic plate descends, it melts, and the resulting magma rises to create volcanoes along the edge of the continent. Over millions of years, repeated eruptions build these volcanoes into major peaks and collectively into continuous mountain ranges. The process also compresses and uplifts the continental crust, adding to mountain building. Subduction-related mountains are often characterized by active volcanism, frequent earthquakes, and rapid uplift. The Pacific Ring of Fire consists largely of subduction-related mountains surrounding the Pacific Ocean. These mountains are geologically young and dynamic, still actively growing and changing. The combination of volcanic peaks and uplifted terrain creates some of the most dramatic topography on Earth. Mountain weather can change with startling rapidity. Morning sunshine can give way to afternoon thunderstorms within hours as solar heating triggers convection. Clear evenings can transition to snowstorms overnight when weather systems move in. Wind speeds can increase from calm to gale force in minutes as fronts pass. These rapid changes create challenges for anyone spending time in mountains. The weather that existed when you started a hike may bear no resemblance to conditions a few hours later. Preparation requires anticipating worst-case scenarios rather than assuming stability. The changeable nature of mountain weather reflects the complex interactions between terrain, atmospheric circulation, and local heating and cooling. Mountains disrupt airflow, trigger cloud formation, and create their own wind systems that operate semi-independently of broader weather patterns. The result is weather that is notoriously difficult to predict and changes more rapidly than in flatlands. The continental divide marks where water flowing down opposite sides of a mountain range ends up in different oceans. In North America, the continental divide runs along the crest of the Rocky Mountains. Water falling on the western side flows toward the Pacific Ocean. Water on the eastern side flows toward the Atlantic, sometimes via the Gulf of Mexico. The divide is not always a simple line. In some places, it splits, creating enclosed basins where water flows to neither ocean but evaporates or seeps into the ground. In other places, the topographic divide and the hydrologic divide do not quite match, with underground water flow crossing beneath surface drainage divides. The concept of a continental divide extends beyond North America. Other continents have their own divides separating drainage basins. These boundaries are fundamental features of global hydrology, determining the paths by which water returns from land to ocean. Glacial flour, the extremely fine sediment produced by glacial grinding, remains suspended in water for extended periods, giving glacial streams and lakes their distinctive milky color. The sediment particles are so small, often just a few micrometers in diameter, that they settle extremely slowly. This suspended sediment can travel far downstream before finally settling out in lakes or slow-moving river sections. The mineral composition of glacial flour depends on what rocks the glacier eroded, creating different colors in different locations. Some glacial lakes appear bright turquoise due to the specific minerals in their glacial flour. Others are more gray or tan. The suspended sediment affects aquatic ecosystems by reducing light penetration and potentially clogging the gills of fish and filter-feeding organisms. Some species have adapted to these conditions, while others cannot survive in glacial waters. High mountain deserts exist in rain shadows where little moisture reaches the ground. The Atacama Desert in Chile, one of the driest places on Earth, lies in the rain shadow of the Andes. Moisture-bearing winds from the east rise over the mountains, losing their water as precipitation on the windward side. The descending air on the lee side is dry and warms as it sinks, creating extreme aridity. Some weather stations in the Atacama have never recorded measurable rainfall since observations began. The landscape is barren rock and sand, with almost no vegetation. Despite the extreme dryness, these deserts can exist at high elevations, where temperatures are cool or even cold. The combination of high altitude and extreme aridity creates unique environments found nowhere else. Life persists in tiny refuges where fog occasionally provides moisture, or in scattered oases where underground water reaches the surface. Mountain timberlines are sensitive indicators of climate change. As temperatures warm, trees can potentially grow at higher elevations than before. In some mountain ranges, researchers have documented upward migration of tree line over recent decades. Seedlings establish above the former tree line, and the forest boundary gradually moves uphill. However, tree line migration is slow because trees near their cold limit grow slowly and may take decades to reach reproductive maturity. In other areas, tree line has not moved despite warming, suggesting factors other than temperature also limit where trees can grow. Moisture availability, soil conditions, and wind exposure all play roles. The response of tree line to climate change varies among mountain ranges and between individual mountains, reflecting the complexity of factors controlling where forests end and alpine tundra begins. The formation of mountain ranges can occur through several different mechanisms beyond simple plate collision. Volcanic mountains build from accumulated lava and ash. Fault block mountains form when crustal blocks are uplifted along faults. Plateau mountains result from broad regional uplift. Erosion can also create mountains by removing softer rock and leaving behind resistant peaks. Many mountain ranges form through combinations of these processes. The Alps formed through collision, but also involve folding, faulting, and volcanic activity. Understanding the specific mechanisms that created any given mountain range requires detailed geological study. The end results may look similar, with high peaks and steep slopes, but the underlying processes and rock structures differ significantly. These differences affect how mountains evolve over time, what resources they contain, and how they respond to erosion. Mountain caves preserve some of the most complete records of past climates. Cave deposits called speleothems, which include stalactites, stalagmites, and flowstone, form as water drips through caves depositing dissolved minerals. The rate of formation and the chemical composition of speleothems vary with temperature and precipitation at the surface. By carefully analyzing speleothems, scientists can reconstruct climate conditions going back hundreds of thousands of years. The layered structure of speleothems provides precise dating through uranium series methods, allowing correlation of climate changes with specific time periods. Some mountain caves contain continuous records spanning multiple glacial cycles, offering windows into past climates that complement ice core and ocean sediment records. These cave archives are particularly valuable because they exist in continental interiors where other long climate records are rare. Katabatic winds, dense cold air flowing downslope under gravity, are common in mountainous regions. At night, mountain slopes cool through radiational heat loss. The air in contact with the cold surface also cools, becomes denser, and flows downhill like water. These gravity-driven winds can reach substantial speeds on steep slopes, particularly when strong temperature inversions develop. Valleys become rivers of cold air draining downward. Communities in valley bottoms may experience persistent cold downslope winds through winter nights. In some regions, katabatic winds have local names and are well-known features of the climate. These winds affect frost formation, pollution dispersion, and the distribution of cold-sensitive plants. They represent one of many ways mountains generate their own distinctive wind patterns, independent of broader atmospheric circulation. The jagged, serrated ridges, characteristic of many young mountain ranges, result from active erosion by glaciers and streams. Ridge crests erode from both sides simultaneously, gradually narrowing until they become knife-edge arcs. Glaciers carving valleys on opposite sides of a ridge steepen the slopes and sharpen the crest. In some cases, the ridge becomes so narrow that it is barely passable, with sheer drops on both sides. These sharp ridges contrast with the rounded, gentler ridges of older, more eroded mountain ranges. The Appalachians, worn down over hundreds of millions of years, have mostly smooth, rounded ridges. The Alps and Rockies, much younger, retain jagged crests. The transition from sharp to rounded reflects the cumulative effect of erosion over geological time, gradually softening landscapes and reducing relief. Mountain ecosystems provide numerous services beyond their obvious beauty. They regulate water flow, storing precipitation and releasing it gradually. They harbor biodiversity, providing habitat for countless species. They influence climate through their effects on atmospheric circulation. They provide resources, including timber, minerals, and hydroelectric power. They offer recreation opportunities that benefit human physical and mental health. They hold cultural and spiritual significance for many communities. The economic value of these services is difficult to quantify, but undoubtedly immense. Protecting mountain ecosystems protects these services, ensuring they continue to benefit both mountain residents and people far downslope who depend on mountain water, biodiversity, and climate regulation. Some mountains have been shaped as much by ice as by tectonic forces. The Alps, for example, formed through plate collision, but were then heavily modified by glaciation. During ice ages, massive glaciers covered much of the range, carving the sharp peaks, deep valleys, and broad basins that characterize the modern Alps. The Matterhorn, though formed by tectonic uplift, owes its distinctive pyramidal shape to glacial erosion. Without the ice ages, the Alps would look very different, probably more like a plateau with gentler relief. This interplay between tectonic construction and erosional sculpting produces the landscapes we see today, with each process contributing to the final form. Temperature lapse rates, the rate at which temperature decreases with elevation, average about 6.5 degrees Celsius per 1,000 meters in the troposphere. However, the actual lapse rate varies depending on humidity and weather conditions. Dry air cools at about 10 degrees per 1,000 meters as it rises and expands. Moist air cools more slowly, around 6 degrees per 1,000 meters, because condensation of water vapor releases latent heat that partially offsets the cooling. These lapse rates determine how quickly you experience colder conditions as you climb. They also affect cloud formation, precipitation patterns, and the elevation of snow lines. Understanding lapse rates helps predict where snow will fall versus rain, where freezing levels occur, and how temperature varies across mountain terrain. Thank you for wandering through the ancient world of mountains with me tonight. As we traveled together from one peak to the next, we saw just how patient and persistent the forces shaping our planet can be. Mountains of stone reaching toward the sky, peaks that have stood for millions of years, yet continue to grow and shrink in a dance measured in geological time. Slopes that capture moisture from the sky and release it as life-giving water for the valleys below. Every mountain a different story. Every peak a marker of time far beyond human measure. If you enjoyed this quiet journey through the high places of Earth, I invite you to like, subscribe, or share a thought below. It helps other curious dreamers find their way here, one sleepy soul at a time. But for now, let all that rest. Let your breathing slow. Let your mind settle like snow on a mountain slope, soft and still. The mountains will keep standing without you for a while, patient as always, holding their stories in silence. You have done enough for today. Close your eyes, rest, and dream of high places where the air is thin and the world stretches out below in peace. Good night.